I first heard about Sebastian's work when I was doing my PhD on information extraction, and I came across his paper on universal schema relation extraction. And I found it really, really fascinating and thought, wow, I want to work with this guy at some point. And luckily, I got to work with him during my postdoc. We had worked on a project on scientific information extraction. But since then, he's also done some other great work. So in fact, his focus the last few years has mainly been on combining symbolic AI and neural approaches. And in this area, he's also proposed some seminal methods, including a neural program interpreter, as well as methods for injecting logical rules into deep learning models. Sebastian is also one of these rare researchers who doesn't just manage to have an impact within research, but also actually has an impact in the real world. So he's co-founded 2 startups, one on fact-checking called Facmata, which got seed funding from Google, and one on machine reading called Bloomsbury AI, which was bought by Facebook last year. Accordingly, he at the moment splits his time between his research group at UCL and the research team he manages at Facebook AI London, or as I've been told to call it, how was it called? Instead of managing? Supporting, yes. Okay. Without any further ado, please enjoy this talk by Sebastian, which I've heard will be a little bit controversial.
Thanks so much for the kind words, and thanks for having me. Let's move this around. Can you hear me okay? All right. All right. Should get better. I speak usually too loud. So, speaking of controversial, the title of this talk is actually not very appropriate for no other reason that it's actually not that related to what I talk about, but I'll still give you the backstory to it. So when Andrew and Isabel and Samir asked me to come and talk at AKBC this year, this was a couple of months ago, and I was in this transition period, A, because our startup had joined Facebook, but also B, because BERT just happened. And BERT got me really excited in many ways, and so did Elmo, but also a little sad, because I felt AKBC should have been BERT, right? And it wasn't. Like, the idea behind AKBC in many ways is to, solve this problem of the knowledge bottleneck in AI and help downstream agents to do many more things and do much better in a lot of things. And as many good applications of knowledge-based constructions there are, I don't really feel it has done that in the same way that in the last year, things like Elmo and BERT have done it. There are a lot of benefits and advantages to, I think, the way that we generally do it, but still it got me a little sad because I feel like we didn't really reach that point. And so I started to think in my head about how to, decompose what we do in AKBC and see how something like BERT cannot just fit in there and help us, but maybe even redefine how we do things. And I had, I'm sure, very deep thoughts about how to deconstruct automated knowledge-based construction and reconstruct it in interesting ways, just never really got to finish those. So I think this talk is more aptly called something like an exploration of methods that do things like AKBC, but maybe without being as explicitly graph-like as we usually go about things. And I think that's the more appropriate title. So I hope it will still be somewhat interesting. So let me start by talking a bit about knowledge-based construction, not because I think you need to know what it is, but just to ground, the whole of this course, the whole of this talk, and the examples and all of that in one story. Also to remind you who won this is probably not very readable. Who won the 2018 Turing Award, which are 3 people. One of them matters to us. How do you answer such a question in AKBC? Well, maybe you turn it into a semantic form or some kind of triple with a hole in it, and then you execute that query or that semantic form against a knowledge graph, and then you come up with the answer, Jan LeCun. And that's part of the story. The real part of the AKBC story is that usually the graph here is incomplete. We just don't have enough knowledge. People haven't entered that yet. So what we have to do is maybe read a couple of documents, then apply our NLP pipeline to it, find entities, co-reference, relations, produce more triples, and then feed them into the knowledge graph. In a nutshell, I think that's what a lot of AKBC is about. And I think this can work great, but there are a couple of, at least, problems or challenges. One of the challenges is that you need quite a bit of annotation to get this pipeline right here. And there will be noise, there will be cascading errors. And even though we got better over the years in doing this, I still think for a given domain, given new problem, getting this right is really hard. And there will be a lot of noise at that stage of this whole story. The other problem is that usually you have some type of fixed schema here, which might work for some use cases, but then you have new questions and you have new problems and you have to rethink the schema and this ontology, and that's usually a lot of work, controversial. It's not easy to come up with these schemas, and once you've come up with them, you need more annotation data, and so you're back to square one there. For all of these, we have seen solutions and approaches. So I'm not saying these are not solvable, but still, these are recurring issues in this picture. And then at question time, if you do natural language question answering and you want to use a knowledge-based approach, you again need annotation to train your semantic parser. Obviously, and I think one big argument you can make for the highly structured symbolic representation of knowledge that this picture is conveying, there are a lot of use cases where the questions aren't natural language questions, but they are actually structured questions that come from other machines, and that's really where things kick in. That being said, and just to make this contrast to BERT, even in BERT, I mean, the interface isn't symbolic, it's a bit of vectors, but these vectors are used in other machine applications as well. So I don't think that's a necessary condition for a good AKBC solution. All right, so that's the picture. One of the great things, and I don't know why I'm quoting this, I think this is really true. Generally, this picture is very interpretable. These graphs, you can look at them, you can debug them, you can add things to it, remove things to it. I think that's a great thing. So that's good. Now, the amount of deconstruction I'll do is pretty much this. Usually, this part here is what I would call a reader. So it reads the data and processes it in a way, then puts it into some kind of memory, and then there's an answerer or client that uses that memory to answer questions. And I guess the main idea is to say, or to ask, what are other ways of instantiating this picture? What I'll do in this talk, I'll look at two ways of instantiating this picture slightly differently. I don't think either of these are that new, but I think they're still interesting and worthwhile talking about. So the first part of this talk will focus on how much Elmer and Bird, as is pretty much, fits into this picture. So I'm not talking about how you can use Bird to do better information extraction or better reasoning or anything like this. I'm just wondering, is Bird already an AKBC solution in a way? And the way that would fit into this picture is by saying, well, when Bird reads, it takes a sentence and it's given a lot of masks, randomly, uniformly sampled, that Bird has to learn to predict. And that's the way that Bird is reading input, right? It takes a bit of training data and tries to explain it, or tries to self-predict it. Then the memory, that's how Bird would do this. And then the memory is essentially fed by SGD or some variant of this on this training example. And it represents the data in a fully distributed manner, right? So there's no more graphs. The only thing that knows in this context is the set of parameters in Bird. So that's some form of, I'd say, you can think about it as an auto-associative or distributed type of memory. And then, at least for the case of these natural language questions, or also structured questions, one simple way we can query BERT is just to take these questions and turn them into what is called closed questions, essentially statements that have the answer masked out. So for example, if we have the question, who won the 2018 Turing Award, we can turn this into mask won the 2018 Turing Award. And then we can ask BERT as such, please fill in this gap. That's one way of interacting with the knowledge in BERT. It's not the actual standard way, because in practice what you do is you use the representations that come out of it, or you fine-tune it. So I'm not saying that's the only way that BERT serves as a knowledge source here, but it's one way that we can quite directly test, without any further training, what knowledge is in there. And then you get the answer. So what I like about this picture is that there's really no annotation at all you have to do on the reading side. So it'll just, you can probably, and if you're more clever about it, be a bit clever about what you're masking and maybe use NER for that, but we found that, at least so far, that isn't even necessary. There's also no strict schema here. Basically anything that you can shove into there, you could probably talk and ask it about, which is great. And at least for this particular application, it's a little hard to read, you don't really need much annotation to translate sentences into questions, or questions into sentences. That is not a very hard task. So that's good. There are definitely drawbacks, and I think one of the main one is that it's really hard to understand what's happening here, and even when you get answers right here, you might not be right for the right reasons. Like, you might just be guessing it. And maybe you're really good at guessing, but somehow it doesn't seem that attractive to get these answers right all by guessing. All right, so that's, I think, part one. Sorry, when did I start? Because I started a bit later. Okay, that's good. So that's the first part. In the second part, I'm going to look at a different picture, namely what I call the information retrieval and machine comprehension picture, where the idea is to say reading is essentially a no-op. You just take the document and you feed it into your memory, which is a collection of documents plus some kind of index, right? Like an information retrieval index. And then when you have a question, you first do information retrieval, find the right documents, and return these documents, then use some kind of neural question answering model to answer the question directly on that document, and then you return the answer. So a different way of achieving the same goal with a couple of benefits, like the reader now needs, what I wanted to say, this is, I think, related to what Chris Manning always called as sort of text as knowledge, right? Like, so you actually don't represent the knowledge explicitly beyond how the knowledge was initially expressed in text, and then you lazily retrieve the relevant knowledge as you need it, which I think is also very attractive. And it's generally great because you need no annotation here, you're very flexible. You do need quite a bit of annotation at the neural QA side in order to train these models to do good question answering. So what I'll talk about, no annotation here. What I'll talk about in the second part will be a bit about how we can reduce the annotation need on this side in this picture. So I'll talk a bit about what we did on unsupervised question answering, which can actually work remarkably well, at least in comparison. All right, so let's go back to Elmo and BERT and ask how it could be used as an AKBC solution out of the box. And this is pretty much just an exploration. We want to see how these models do compared to other ways of doing it, maybe more traditional and relevant to the first picture I gave you. So the way that we answer this question will be following this particular setup. We're going to have a bunch of test facts, which we take from the Google relation extraction corpus and the so-called T-Rex corpus. one is a manually collected data set of texts, mentions of relations, and the actual relations. The other one is automatically constructed, but they have pretty much the same structure. So the structure is like this. You have this set of triples, just your standard Obama was born in Hawaii, etc. And you have a bunch of documents. And we have a link from the triples to the documents in that we know that these documents mention these facts. In fact, we know that these sentences, specific sentences in these documents, mention these facts. And the first thing we'll do as a baseline is we're going to ask a knowledge-based population system, essentially based around the relation extraction system by Sorokin and Gurevich in 2017. We asked that system to take all of these mentions of these facts, and we give them only those mentions, so we don't give them any chance of producing noise. We only give them a mention of these facts and produce a knowledge graph from them. And then we're going to use the same documents plus some more to train Elmo and Bird. And in fact, we don't train Elmo and Bird, we just take the off-the-shelf Elmo and Bird solutions that we can download from the web. And then we take particular facts, and for each of these facts, we're going to ask the KVP model, what do you think is the answer to this fact? And we're going to ask the Bird model, based on a template that we created for this particular relation, to fill in the gap in this mask. And then we calculate things like position at 1 and position at 10, and compare these two values. As I mentioned before, Bird here in Elmo is trained off the shelf. It's taken off the shelf, which I think is interesting because we just want to know what is in these knowledge bases right now. It's also good because it has a low carbon footprint. We don't have to retrain Elmo and Bird on a lot of things. So that's something worth keeping in mind. All right, when we do the knowledge-based population, we try to give the knowledge-based population system a helping hand, in particular in terms of co-reference and entity linking. So rather than implementing a complex entity linking system, we say, well, for any given sentence where we know the facts are expressed in, if, say, the fact that you need to extract is LeCun won an award in 2018, the relation extraction or KVP system gets a reward, gets perfect accuracy, if it finds any relation in that sentence that has the same relation type. So if you find that Turing won a 2018 award, then that would still be considered a hit, an actual correct prediction by this KVP oracle. So that was just to make sure that we're not making it too difficult for the KVP. I think we also had a very simple entity linking heuristic that we also tried, which doesn't work nearly as well. But this was a way to make sure it really has the best possible setup. So yeah, that would be a correct answer. And so we're going to look at these two data sets that I mentioned, the Google RE one and the and the T-Rex data sets. Pretty similar in shape, just one is automatically constructed and one is manually constructed. And we look at a couple of baselines. One is just a frequency baseline. The other one is KVP using a very simple form of entity linking. Then we have the KVP oracle that uses this oracle form of entity linking. Then we have Elmo, and then we have Bird. And we do this for these two data sets. One thing I need to stress is that all the questions that we looked at, and I think that's a big shortcoming at this point, all the questions that we looked at are single token questions. Because it's not obvious how in Bird you fill in multiple token questions or multiple token masks. We have some possible solutions to that, but all of them require a bit more fiddling and maybe a bit of tuning, and these are all things we didn't want to do in this instance of the research. So let's look at the Google RE corpus, frequency, and let's look at position at 1. Frequency baseline does okay-ish, if you like, with about 5-ish percentage points. KVP did terribly. And that's KVP with our very bad form of entity linking. It got much better with the KVP oracle that we had, but still not that good. Elmo also didn't do that well. BERT did a bit better than the KVP oracle, which I thought was already remarkable. I don't know what's more remarkable here, the fact that when I use an out-of-the-box relation extraction system, it doesn't work that well on a corpus like this. This was the same kind of corpus. I mean, it was the corpus or the type of corpus that the KVP system was trained on. So it was Wikipedia. It was nothing weird about it. It was the same kind of relations. So it just missed quite a lot. And that's what we're seeing here. Again, I'll talk about that later. There's the single token angle here, where this is, I think, where we really give the BERT system quite an advantage, because it's relatively easy to predict single token answers because they're quite frequent. And when there are multiple tokens, KVP will work as good, meaning not so good, but still better than the BERT system. But anyway, let's move on. The T-Rex results were a little better, where the frequency baseline still outperformed the KVP baseline, but the KVP oracle was much better. So to be fair, the Google IE, there were only 3 relation types in there. One, it was all of the models were doing really badly, and that had really, driven these results down. T-Rex had a much wider set of relations, so I think this is a much more accurate estimate of how good these methods are. All right. Elmo didn't do as well either here, but BERT almost matched the performance of the KVP oracle, which, again, I thought was very promising. And again, that's an off-the-shelf BERT, and that's an off-the-shelf relation extractor with a lot of help, which I think is remarkable. Other things you can do with BERT that aren't as clear how you do this with any off-the-shelf tools I can download right now is testing common sense knowledge. So we did the same type of closed question completion for ConceptNet and found that BERT is actually fairly good at predicting, and maybe that's not so surprising because I think most people have that sense already, that there's sort of common sense knowledge within BERT that it's capturing, and it's capturing it quite well. The other thing we did is the same kind of idea, but in the context of question answering. So we looked at this second picture I gave you, the IR plus neuro question answering solution to doing this type of question answering, and try to compare it to that. So we had a couple of test questions, say squad, and we had a couple of documents that mentioned these. And we took questions out of these test questions and then transformed them manually to a closed question at this point, just to test how well these things do. Then we used Dr. QA, one of the sort of standard solutions to retrieval plus question answering, and use this plus some kind of index to answer the questions. Calculate precision at 1 as well, and precision at 10. And then we did the same thing with BERT and Elmo again. And here we found that for precision at 1, there is quite a difference between the accuracy of Dr. QA and BERT. It's substantially better. But the minute you look at precision at 10, for example, both are actually fairly close, which I think is promising. If you think about it from the perspective of in reality, you would use BERT probably in that you use the vectors that are coming out of it, and you do something downstream that you train using these vectors, or that you then fine-tune using these vectors. And if in the top 10 solutions that are somehow in the knowledge of BERT, the right answer is in, a bit of fine-tuning might help you to actually extract that out. So I think this is still quite promising. Again, this was just using BERT out of the box, not at all designed to do question answering. Just to give you a couple of examples of what you can fill in with it, So what you see here are the questions, or the closed questions, here the answers. I think you look at those, and in many cases you feel, yeah, but I don't think it knows. It just guesses because, you know, Adolphe, I don't actually know how to pronounce this properly in French, but that certainly looks like a French name, and hence Paris is probably a good bet. iPod Touch, right, it probably has been seen so often together with Apple. It doesn't know that it was produced by Apple. It just knows that if you ask me for some kind of company in the vicinity of iPod Touch, then it's probably Apple, and that's what it returns. And that's, I think that's fine. So the lower bit here is essentially common sense questions that BERT answers relatively well as well. And you see that the bolded names here, these are the correct answers. But if you look at it, I think most of the answers are also correct. So I think the estimates that we have in terms of how well it does, they're actually underestimates. All of these seem like reasonable, or mostly reasonable answers for common sense questions, which again, I think is really nice. Now, as I mentioned, I think the recurring question is like, do they really know, and can they know? Like, why can language models actually, can they really remember rare facts, for example? Like, if you only say something one time, like, would it remember it? Like, it can't, right? Like, for that, we definitely need a specific extraction tool. And I want to point you to one of the experiments, not by us, but by Kalini et al. In 2018, where they set up a Wikipedia language modeling corpus where they trained an LSTM language model on, and then they added one more sentence to that corpus, which is the random number is that random number. And then they tried to recover this at test time, and it did. Like, it did remember this random number, like, literally as the highest scoring solution by quite a bit off here. Which I think shows you that, I mean, I don't think it's necessarily true that these things can't remember, like even rare facts. I think there are a lot of things going on here that I think we have to disentangle, but I still think that's also promising. Now, coming back to this question of guessing, so do they actually know, or do they guess? One way that we try to answer this question is by looking a bit into correlations. For example, the correlation with the precision at one and the frequency of the subject. And so this is the person correlation between these two. And there's very little correlation between that. So it doesn't matter how often you see the subject. It will remember or not, but there's no correlation with that. So that's kind of promising. What is more concerning is the fact that there is quite a bit of correlation with the frequency of the object. So if it's a common object, you get it much more easily right than if it's an uncommon object. And I think that resonates with, I think, our expectations probably for what these things do. I don't think that's unsolvable. Like, I think it, in the same way that we can somehow remember high frequency subjects, low frequency subjects with high frequency objects, at least I think we can do the opposite. Like high frequency subjects with low frequency objects should also work, but maybe not the combination. I don't know. The other thing we wanted to know is, like, how much does BERT know that it knows? And one way to test this is by checking the correlation between the log probability of the best solution with the precision of that solution. And these things are highly correlated. So, and you probably didn't catch it, but if you look at the examples that we predict, when you're not quite right, usually your log probabilities are lower. I mean, by quite a bit. So, which means that you can actually filter out and get quite explicit knowledge, a quite highly accurate knowledge out of BERT at this point, which I think is also good. I think I was very ambitious with the second part of my talk. So how many minutes do I have left? Okay. Okay, thankfully this was all coherent as one part, so I'll leave it there. But anyway, so one of the questions that we haven't addressed is how do you deal with this in the context of multi-token masks to fill? So a lot of questions like this one, they require you to say San Francisco and not just a single token. And you can come up with a lot of ways to do this within BERT, but none of them really worked so well out of the box. What we're currently leaning towards is essentially having a unidirectional model that is somewhat conditioned on the rest of the sentence, but in which you generate the actual filler of the mask left to right. So like here's this mask, and the mask is going to be filled with this particular left to right sequence of tokens, where you have an end of phrase token that concludes the mask filler. And that seems to work. It does need some kind of fine tuning as well. All right, so let me conclude, as if I knew. All right, so let me conclude and say that I think BERT is actually a fairly good automatically constructed knowledge base, at least for the case of single tokens, which I think is cool. It knows when it doesn't know, in the sense that like precision is quite well correlated with log probability. And again, this is all out of the box. It recovers facts even if the subject is seen very rarely. But it does require to see the object relatively frequently. I mean, the correlations are definitely there. And I think right now, the experimental setup, because we're looking at single tokens, is almost like, it's even hard for us to look at examples where the object is infrequent, because every answer that is just a single token is most likely a very frequent thing, which means we have to look a bit beyond that. And I think it's still unclear a little whether it guesses or knows and what that even means. Like people, when they hear this, they always say, it does a really clever type of fine-grained entity typing. Right, like it sort of sees, oh, in this context, I think I'm looking for a city, and this context looks like it's a city that is related to French people. So maybe it's a French city, and then maybe it looks like it had a capital type of context, so maybe it's Paris, but it doesn't really remember that Paris is the capital of France. And I'm not quite sure how to answer these questions really, or how to argue against them, but I think they're interesting to raise. So with that said, let me finish here. Yeah, Andrew. Dude, that was so high. I had to. Yeah.
Oh, Sebastian, I'm so happy to see this talk at AKBC. Indeed, the time is right to consider things beyond grass. So I've been quite taken thinking about more information retrieval-based way of knowledge bases, and that's not completely distinct from BERT either, because BERT has mechanisms can be used to do that. And one advantage of the information retrieval method is that you get some direct provenance, or like every answer is why.
Yeah.
So one thing I'm wondering is, did you see evidence that maybe one reason that has not been working well is not that it wasn't able to find the right thing was there, but that the answer was not given so succinctly in text. There was no one sentence that really gave the answer, but that somehow BERT is able to, integrate some global information to give the answer even when it wasn't stated succinctly.
I think that's how I would think about it. Yeah. So sorry. Yeah. Yes.
Okay.
The letter. So you mean like why does IR sometimes miss the answer, or an IR-based approach?
Yes.
Yeah. So like I haven't looked at the actual error cases in that way, but definitely BERT has this benefit of just seeing a lot of signal that isn't just that single bit. It's just a lot of things that accumulate that then make you feel the answer should be.
In a way that like the extra part is like some type generalization, or it's actually, you think, like integrated three pieces of information that otherwise would have had to go into some chain?
No, I'm not sure about that. I don't think it does sort of multi-hop reasoning as such, and aggregates these things quite explicitly. I just see it's this signal that's emerging, At this point, yeah, that's a great question.
Unfortunately, we'll have to move on now because we're running a bit. Yes, I know. You can ask all of your questions in the break.
All right.
Yes, thanks, Sebastian.
Okay.